As a physicist, I studied two theories of gravity in university. Two theories about why things fall to the ground. Because Newton and Einstein both noticed that, worked on it, and had something to say about it. We, their foolish descendants, now able to describe why apples fall to the ground and what happens if they fall into a black hole, we are left behind with only one question to answer. Who is right, Newton or Einstein? Whose theory of gravity is correct? To get there, we need to talk about some weird parts of Newton's theory that I bet you've never heard of. So before you go and discourse about your favorite theory of gravity during your next dinner party, you may want to watch how Newton's gravity actually works. First, we should mention that Newton and Einstein didn't come up with their theories all by themselves. Like always in science, they relied on the work of others. Work was spread by others, and they worked with others. After thinking hard, staring at equations and applying some magic, both came up with some decent theories to describe gravity. With Newton's theory, you can predict how Earth moves around the Sun and how fast your rocket has to move to leave Earth. And with Einstein's theory, you can predict black holes and gravitational waves. Since Earth still moves around the Sun and our Milky Way around a black hole, both theories seem to be pretty decent. However, Einstein's general relativity is newer, and newer equals better when it comes to scientific consensus. So Newton can't be right, right? Let's look at Newton's gravitational law. It describes how strongly two objects pull on each other, whereby object is just a fancy physics word for basically anything, like donut or human. The fancy physics word for pulling on each other is force, shortened by F. Its strength relies on the distance of both objects and their masses. The heavier the objects, the stronger their pull. The greater their distance, the weaker their pull. Actually, a lot weaker. All scaled by the gravitational constant, which is a fixed number determining the strength of gravity compared to other forces. Great! That's all rainbows and sunshine, or rather donuts and humans attracted by those donuts, but there's a drawback. First of all, the equation is only valid for point-like masses, which is just what it sounds like, an object having the size of a point. So no more donut, just the mass of a donut condensed into one point. Physicists love this approximation, because it makes calculations so much easier. If you'd be correct, you'd have to split up the donut into point-like objects and calculate their attractions to one another, and to the point objects of the human. Physicists aren't used to so much attraction, and jokes aside, no one wants to calculate that. Luckily, thanks to Gauss, we know that a perfect sphere with evenly distributed mass generates gravity just like a point object. We're happy with pretending everything is a perfect sphere, since small and light objects like donuts and humans generate no noticeable gravitation anyways, and large objects like planets are at least close to being spherical. If you stand on our planet Earth and drop things to the floor, you notice that they speed up. The fancy physics word for speeding up is called acceleration. The acceleration due to Earth's gravitational pull is called general gravitational acceleration. It is the same everywhere on Earth. You can measure this acceleration by measuring the time it takes for an apple to hit the ground. Or you could apply math magic and calculate it using Newton's gravitational law, Earth mass, Earth radius, and the gravitational constant. You would find that the resulting number is just g, the gravitational acceleration. Alright. Approximating objects as being point-like or perfect spheres is yay. So Newton's theory is incorrect in the sense that we have to make some assumptions about reality that are not correct, but it's correct enough to make good predictions about reality. Well, until the things we're talking about become heavy, very heavy. Heavier than Earth, heavier than Sun, more like as heavy as a neutron star or a black hole. Or the objects become fast, very fast, close to or at the speed of light, like elementary particles, among them photons, which are basically light. This is where Newton's theory completely fails, and where general relativity comes into play. Here things become very complicated. Space and time are treated as one. Thereby space is not just outer space, but the fancy physics word for anywhere, any place, or basically the whole universe, And most of the time, time is just time, but it may act counterintuitive, just like space. As if things weren't complicated enough already, the resulting space-time is shaped by the masses of objects that live in it and in return determines how gravity acts on them. If you want to learn more about this, please leave me a comment below. If you only wanted to calculate the attractions donut or Earth has on humans using general relativity, you would start by making some simplifications. Like, they are neither heavy nor fast on the scale of the universe. You would plug these assumptions into the equations, do some math, and a few approximations down the road, you would end up at Newton's theory again. So Newton's gravitational law is a simplification of Einstein's general relativity. It is correct under some assumptions, but it's incomplete. This stacking of theories is actually an inherent feature of science and physics. So the answer to our question whose theory of gravity is correct is Einstein's, right? Well, yes, based on our current knowledge. However, there are clues that it's not complete, just like Newton's theory is incomplete. Some of these clues are the weirdness of dark energy and dark matter, as well as the information paradox, or how general relativity is not unified with quantum theories. Physicists are hoping that someday they'll find a grand unifying theory which explains all of those things. Meanwhile, at dinner parties, we should enjoy chatting about the beauty of Einstein's unbeaten theory and the straightforward application and surprisingly broad extent of Newton's theory. If you are curious how it even allows us to tackle the surprisingly complex task of weighing someone's mass, check out this video. Thanks for watching. Please drop your questions in the comments and subscribe to find out how it actually works.